Chapter 14 is about liquids and solids. We just finished a whole chapter on gases. This chapter is shorter, and we're not even going to cover all of it. First, let's talk about, review some things that we know. We talked about the states of matter earlier in this semester, and we discussed how gases have very low densities. They're highly compressible, and they expand to fill the container that they're in. Here's an illustration of a gas. And now that we've talked about gases, we understand their particles are in constant random motion. They travel in a straight line till they bump into something and they exert a pressure. And the reason the gas is compressible is because there's all this empty space between the particles. And so you can just push the particles closer together and compress the gas that way. Solids, on the other hand, have much higher density compared to gases. Here's the illustration of a solid. And we can see why they have a higher density. There's basically very little empty space between the particles. You can't put round things together without having some empty space, but these guys are touchingly close. Solids are slightly compressible. Some books say they're not compressible. Basically, you cannot compress a solid. And solids are rigid. They retain their shape regardless of what container they're in. And that has to do with the forces that are holding these particles together. Liquids are kind of in between. Let's look at what happens in the transitions between these states. If we take water at minus 20 degrees Celsius, and here on this graph, temperature is increasing on the y-axis, and the x-axis is representing heat that we're adding to this sample of ice. So the water at minus 20 is frozen. As we add heat to it, it warms up. That makes sense. When you heat something, it gets warmer. When we get to the melting point, now the ice starts to melt to water, it transforms from a solid to a liquid, and while that transformation is occurring, the temperature does not rise. It remains at 0 degrees Celsius until all of the ice has melted. Once the ice has melted, then the temperature increases again until we get to the boiling point, which is where the transition between a liquid and a solid occurs, and the water boils and is converted into the gas state, which we call steam. And the temperature there will stay the same until all of the water has been converted to steam, and then the temperature of the steam can rise. From that table and from other information, we know that the normal boiling point of water is at 100 degrees Celsius. And this is a number that you should know. I don't make you memorize a lot of numbers, but the boiling point of water is 100 degrees Celsius. The freezing point of water is 0 degrees Celsius. And these are the numbers that, they're the temperatures that were used to generate the Celsius temperature scale. It's based on the freezing point of water being 0 and the boiling point being 100. Another thing that you should know is that the density of liquid water is 1. You're like, wow, there's a lot of ones and zeros and nice round numbers here. Those aren't coincidences. 1 gram per milliliter. The units gram and milliliter were designed so that the density of water is 1 gram per milliliter. Because we have to have a point of reference. And so they chose something that's very common, that's easy to work with, and that's water. Water's everywhere. Water is one of the few compounds that is widely present in its liquid state at room temperature. Most compounds are solids or gases. There are very few pure substances that are found as liquids. An interesting thing about water is that in the solid state, which we normally call ice, the density is actually a little bit less. And what that means is that ice cubes float. Here's my rock star with the ice in it. All the ice goes to the top. because the density of the ice is less than the density of water. And we don't think that's unusual because we're accustomed to that. But for most substances, the solid is more dense than the liquid and will sink in its liquid. That's normal. This behavior of water is not normal. It's a good thing because I grew up in Minnesota, and tourism is a big thing there, and fishing. Minnesota's the land of 10,000 lakes, which is actually an understatement. There's more than 10,000 lakes up there. But in the winter, it gets really cold. Here in Central California, we have no idea what cold is. There were some days when I was a child where the absolute temperature, the actual temperature, not wind chill, was minus 40 degrees Fahrenheit. 40 degrees below zero. So that's cold. So the lakes freeze there. And they, in fact, freeze so thick that they used to lay train tracks across the lake and move timber in the winter when they didn't have to snake around all these lakes. Occasionally, trains fell through because they used them too long. But anyway, but the ice forms at the top. If ice was more dense than water, than the liquid, like most things are, as the ice formed, it would sink to the bottom of the lake, and all the lakes in Minnesota would freeze solid. And then what would happen to all the fish? They would die. They would die, and all the other things that live and survive in the very cold but not frozen water under the ice would die. A bad thing about the density of ice being less is that when water freezes, it expands. And so if you've ever thought you were going to be real clever and put your can of soda in the freezer to cool it down, or, I'm going to be out tomorrow and it's going to be really hot, I'll just put my unopened water bottle in the freezer and freeze it, and then, it'll stay cold all day. Is that a good idea? What happens to it? It breaks open, right? Even a can of soda, it's an aluminum can. It'll pop open because as the water freezes, it expands. And this causes pipes to break when they freeze. So you have outside pipes, and if the water inside freezes solid, it can actually break metal pipes. Freezing water is actually a very powerful thing. But that's an unusual thing about water. Water, actually, there's a lot of strange things about water. And this section is titled Water and Its Phase Changes. Okay, so thinking back to that temperature heating curve, during the process of melting ice by adding heat, what happens with the temperature of that ice liquid water slurry or mixture? Does it stay constant? Does it increase? Does it decrease? Or is it not predictable? Let's go back and look at the graph. This little purple line here, this is the period in which the ice and water are both present. What's happening with the temperature there? It's staying the same. Because as we're still adding heat. Why isn't the temperature going up? All the energy, the heat energy that we're adding, is going into the process of melting the ice. And so when you have an ice and water mixture, it doesn't matter how long the ice has been in there or how cold the ice was before you stuck it in the water, the temperature is going to be 0 degrees Celsius or really close. Now, 2 weeks ago we did a lab where we made ice cream, and we took the temperature of the ice before we put some salt in it. What was the temperature of the ice? It was close to 0. And some people had like 0.8 or 1, but it was really close to 0 because that's the temperature at which ice melts. If you have not pure water, or if the atmospheric pressure is higher or lower than 1 atmosphere, that can change the melting point slightly, but it's going to be 0. And the other thing up here, let's think about cooking, making a pot of spaghetti. You put a pot of water on the stove and you need it to boil, right? So maybe it starts out here around 25 degrees Celsius, around room temperature, and you put it on there and you crank up the burner and it heats up and it heats up and it heats up. Once it starts to boil, the temperature doesn't go up anymore. If you wait and let it boil for 10 minutes, the temperature is the same. This is not something that we would notice, right? Because who goes around taking the temperature of the boiling water in their kitchen? You know, science geeks do, but not normal people. Yes?
Would it have indicated that it was the ice and water stage? Because I thought it was asking about when it was going the blue line, when it's just liquid water.
Okay, in the question, it did indicate that it was the ice/liquid water slurry, and they mean mixture. So when there's water in the liquid state and ice, which is water in the solid state, present together, the temperature will be 0. So which letter is the correct answer here? A. Another question? No? No? Okay, that's the end of that section. Any questions about that?